Hi, welcome. In this video, we're going to do some CPU scheduling practice, first come, first serve, and shortest job first, non-preemptive. So let's get started. So let's just review our scheduling algorithms. We have non-preemptive algorithms, first come, first serve, shortest job first, and priority. We have our preemptive algorithms, round robin, shortest remaining time, and preemptive priority. Starvation can happen in any system in which you have lower priorities starving for CPU time, and that's because if you have any priority based, so shortest job first, priority, shortest remaining time, and preemptive priority, they are all priority based. So if your system keeps having high priority tasks, those lower priority tasks can get moved to the back of the queue and starve for CPU time. Aging can be used. That's just a technique that after processes sit there waiting for a certain amount of time, maybe bump up their priority and give them a chance on the CPU. In addition, we're going to talk about shortest job first. And there's a prediction formula for the shortest job first because although shortest job first can give very good results in terms of waiting times, it is not practical because processes you do not know how long a CPU burst is going to be when a process gets admitted into the system. They don't have CPU bursts, they don't have a tag that says this is exactly how long the CPU burst is going to be. So there is a formula that we're going to practice for predicting the length of a CPU burst based on previous CPU bursts. So let's get started. All right, so just to review the calculations, we have the CPU utilization. That's the amount of time that the CPU is actually active, the percentage of time. So if you have 100 time units and the CPU is active only 80 of those 100 time units, that would be at 80% CPU utilization. We have turnaround time per process. So each process, you calculate the turnaround time from the time it gets admitted into the system until it exits. Then you can also calculate the average of the turnaround time. So turnaround time, wait time, and response time, you would calculate per process and also the average. Right, so I can just go over this, but the best way to do it is to do some exercises to understand how this works. So remember that the ready state, that is where waiting time is accumulated. Also, that is just to remind you how often the CPU scheduler is working. Every time a new process gets admitted or an interrupt happens or an event is completed, the CPU scheduler is always working. Remember that the response time is only a one-time measurement. From the time it gets admitted to the first time in the ready queue, the response time is the first measure of waiting time. The waiting time is the sum of the time spent in the ready queue, and turnaround time is the total time active in the system. All right, so let's get started. So here's first come, first serve. Here's an example. This is a Gantt chart. So this represents the CPU and time. So this would be time 0. And just the way that you look at this, we have 3 processes, process 1, process 2, and process 3. Each of these processes has a burst time. Process 1 has a burst time of 24 time units. You could also add an arrival time. So we're going to assume that all the processes arrived at time 0. However, we're also going to assume that they arrived in this order. So even if they all arrived at time 0, P1 actually got there first, followed by P2, followed by P3. So that's why this is first come, first serve. So let's get started. These calculations we want to do together. So this is the wait time and this is the turnaround time. So let's say, okay, P1 arrived and it has a 24 times units. It spends 24 time units on the CPU because that's its burst time, and then it's done and it exits. So P1's burst time P1's turnaround time is 24 time units because it does only one CPU burst. Obviously, we're going to get more complicated with CPU and I/O, but this is just an overview with a very simple example to understand how to use the Gantt chart and how these scheduling algorithms work. So P1 is done. Now we have P2. P2 is going to get onto the CPU at time 24 and has 3 time units on the CPU, so P2 will be here until time 27. So P1 arrived at time 0 and did not wait at all. P2 arrived at time 0 but waited 24 time units to get onto the CPU. This is how long P2 waited. And then P2 arrived at time 0 and was done at time 27, so P2's turnaround time is 27. Now we have P3. P3 has a burst of 3 time units, so P3 had to wait 27 time units to get on the CPU, and P3 has a turnaround time of 30 time units. So if you add these up and divide by 3, you can get the average. So the average turnaround time is 27, and the average wait time is 51 divided by 3, 17, I believe. So I think on the next slide I do have the calculations. I don't have the results here, but I think that that was right. 51, 17. And the turnaround time would be 27. And so you can use this to compare. So we're going to try the same processes, only we're going to compare them doing shortest job first to demonstrate how putting the shorter jobs first is going to reduce the wait time significantly, because, and it would make sense, right? If you P1 has a 24 time unit, so P2 and P3 have to wait so much time before they get a chance to get on the CPU. Now, the reason we're not doing response time here is because the response time is going to be the same as the wait time because the processes only go on the CPU once. So there isn't any reason. So if I was to ask you, you could say wait time / response time is going to be the same because it's still only their first measure. All right, so now let's try it with shortest job first. So we say shortest job first. We have both P2 and P3 have the same burst time. So since both P2 and P3 have the same burst time, the tie will be broken by first come, first serve. So we would do P2 first. And that means that P2 waited no time and P2's turnaround time is 3. Then we have P3, which P3 had to wait 3 time units to get the CPU and finished in 6 time units. And then we would have put P1 here, where P1's wait time was 6 time units and turnaround time of 30. So you can see the wait time has dropped significantly from 17 time unit average to 3 would be the average wait time using the shortest job first. So you can see how the shortest job first could significantly reduce wait time by putting the shortest jobs ahead of the longer jobs. So why don't we use shortest job first? Well, you can't use shortest job first because you don't know the CPU burst length. Also, shortest job first could cause starvation. Any priority-based algorithm can cause starvation. So shortest job first might not always be, or any priority-based algorithm might not always be the best choice. But if you, sometimes it could be better because then there's a lower waiting time. So how could you implement an algorithm that's similar to shortest job first? Well, you could assign higher priorities to those tasks that tend to have shorter CPU bursts. So it wouldn't always put the shorter ones first, but you could give those tasks that tend to have short CPU bursts could be assigned a higher priority, and then you just use, a priority algorithm. We are going to do some exercises with a multi-level feedback queue implementation that filters out the shorter jobs. And so that is another technique. The third technique is to use the prediction formula to predict based on the previous CPU burst, predict the next CPU burst. So let's just go through this exercise of how the prediction formula works. All right, so here is the prediction formula. So let's just break down the pieces of the prediction formula. So the first piece here is, this is your burst that you're going to be predicting. This is the actual burst that just happened. This is the average of all of the previous bursts that have happened. So if you're predicting T of 2, then this over here would be T of 1. Or say you're predicting T of 5, that would have been the prediction from T of 4. So you use the exponential averaging to start with a T of 0, get the T of 1, get the T of 2, T of 3, T of 4, etc. And then A is a weight. So A is going to determine which is more important. So if you take a look here, you multiply the A times the previous burst that you just did, and you multiply 1 minus A times the average of all the previous bursts that was calculated, and it's going to decide which one is more important. So if A is 0, right? If A is 0, then the last burst has no meaning whatsoever. And if A is 1, then the averages of all the previous bursts is not important. So if A is 0.5, then 0.5 or 0.5, then it's going to weigh on which one is more important. Closer to 0, the last burst is less important, and closer to 1, the last burst is more important. So here is a formula. Of course, if you're going to do this exercise, you're going to be given the numbers, and then all you have to do is plug it in. So here, if we have A is 0.25, so it's closer to 0 than it is to 1, which means if it's closer to 0 than it is to 1, that means that this would be 0.75. So that means that the previous calculations are 0.75 and the last burst is 0.25. So it's just plugging in, it's just math and plugging in. You have to be given the bursts, obviously. So you have to be given the bursts in order to do the calculation, because these are actual bursts, and you have to be given T of 0. So in order to calculate it, you just plug in. So you would first calculate T of 1, which would equal 0.25 times this burst right here, which is 3, plus 0.75 times T of 0, which is 2. And that would give you 2.25. Hopefully I have done the math right. Oh. Okay. Then we want to take 2.25, so you would calculate, because this is asking you to predict T of 3. So T of 2, 0.25, and times 4. If you're wondering where the 4 comes from, this is n plus 1, and this is n. So this is the T of 0 burst to get T of 1, T1 burst to get T of 2, T2 burst to get T of 3. And then you're going to add that to 0.75 times what we just calculated, which is 2.25, and that result will be 2.685. And then to get T of 3, you have 0.25 times 5 plus 0.75 times 2.685, and then the answer would be 3.26. So you guys can double check this. If I made a mistake, someone will for sure let me know, but I believe that is correct. So let's just go over what we calculated here. Let me see my highlighter. Okay, so you want to predict, oh, that's not my, oh, okay, you want to, anyway, this is much neater anyway. Okay, so you want to predict T of 3. So in order to predict T of 3, you, where's my pen? Okay, you have to use, this would be T of, oh, now I lost my pen here. All right, so I will just use this pen. Anyway, so in order to get T of 3, you have to have the 0th burst, T of 1 burst, and the T of 2 burst. You also have to be given T of 0, so then you need to have A. So A is going to multiply times the previous burst. So at 0.25, the previous burst is a little less important than the averaging of all of the previous bursts. You calculate T of 1, then you calculate T of 2, and then you use T of 1 to get T of 2, T of 2 to get T of 3, and the answer is 3.26. So what does that mean? You're predicting that the third, so based on the T of 0 burst being 3, the next one being 4, the next one being 5, you're predicting that the next one is going to be 3.26. All right, so this is CP priority scheduling, and we're going to do this in the next video.